How much energy the sun shines on all planets is connected to the 3D structure of the solar atmosphere, as it is shaped by powerful magnetic fields. For a long time, we have focused on studying 2D images, and mainly from Earth's perspective. Reconstructions of solar activity from any angle are essential for better understanding solar dynamics. As humanity sets its sights on Mars, anticipating the sun's influence on the Martian environment becomes crucial for the success of future missions. In the future, models like this might also be able to inform satellite operations, communication systems, and the safety of astronauts. The Spectral Irradiance of the 3D Sun on Mars theme is building on the foundation of previous FDL work, taking advantage of novel AI methods that integrate data from the latest generation of solar observing satellites. The result is a virtual observatory that allows scientists to probe the solar corona, the outermost part of the Sun's atmosphere, as it extends its reach to Mars.
Hello everyone, we are Spectral Irradiance of the 3D Sun, in short, Spies on Mars. This is our multidisciplinary theme, including heliophysics and machine learning domains. I am Marcela, and together with Christoph, Brianna, Ritu, Gautier, our faculties Robert, Ben, and Andres, we will show our project goals, experiments, and outcomes. Solar activity can impact the Earth, posing challenges for our satellites and astronauts. The sun emits extreme ultraviolet light, in short, EUV, which impacts Earth's atmosphere and can degrade the orbits of satellites, increasing the risk of them falling back to Earth. To protect these assets, it's crucial to estimate the sun's energy emissions in the form of EUV light, known as irradiance. From Mars' perspective, for instance, the solar irradiance influences atmospheric dynamics, including temperature fluctuations and dust storms, contributes to atmospheric loss, and affects surface conditions, impacting both potential life and exploration missions by altering radiation levels and power generation capabilities. Improving our understanding of the sun dynamics and physics can help us to connect it to other stars and star-planet systems. By studying the sun in detail, we create a reference point that potentially improves our understanding of other stars and then planetary systems, contributing to the search for habitable worlds.
The core philosophy of our project is to maximize the science we can do with our current constellation of satellites. Currently, we have a few satellites orbiting the sun with different instruments that don't always measure the exact same thing. We want to use AI to unify them. For instance, 4 satellites are taking images of the sun in extreme ultraviolet or EUV light. However, only one of them is still capable of measuring the irradiance, which measures the energy of EUV light emitted by the sun. Additionally, they don't necessarily take images of the sun with the same wavelengths that we can see as color filters, giving more information on different regions of the sun that have specific temperatures. In order to better understand the sun and its potential impacts on our assets in space, we need more viewpoints with a complete suite of instruments. One idea could be to launch more satellites. However, in this study, we want to explore how we can use AI to learn from all the data already gathered by the existing satellites and build virtual satellites or add virtual instruments instead. These virtual satellites could be placed anywhere in the solar system, giving us an estimation of novel views of the sun. Additionally, by learning the relationship between the EUV images taken by the satellites and the measured irradiance, we will be able to enhance all the satellites with a virtual instrument estimating the irradiance. So here, the question is, can we generate virtual observatories that view images of the sun and estimate irradiance at any point in the solar system, including Mars? To answer this, we apply AI to create 3D model of the sun that can provide multi-viewpoints from anywhere in the solar system, and then give us the possibility to estimate solar irradiance working as virtual instruments.
So in order to generate 3D representations of our sun and estimate solar irradiance at any point in the solar system, we take the following steps in our spectral irradiance of the 3D Sun on Mars pipeline. First, we use 2D images with a set of wavelengths, represented by the different colors here, from multiple spacecraft at different positions in space. Our SunEarth model then combines this information to resolve the Sun as a 3D object. This allows us to estimate physical quantities with density and temperature in the solar atmosphere. From this, the 3D model then provides us with novel perspectives of the Sun, such as unseen views from the solar poles, but also from any point in the solar system. In combination then with a second neural network, which we further developed from previous FDL challenges called MaxAI, we can feed the images from the novel perspectives to estimate the solar irradiance at Earth, Mars, and at any point in the solar system.
Let's embark on a virtual journey through the solar system. Imagine we're in a spacecraft, starting from our home planet Earth, traveling through space, and ending at Wonder Planet Mars. Imagine the screen in front is our instrument panel, where the left element shows our current location in the solar system. On the right, we have a live view of the Sun from our spacecraft, which changes as we move around it. On the lower left, there is an irradiance meter that tracks how the Sun's irradiance changes as we move through space. This varying irradiance, represented as a full spectrum graph, is a key result from our SPICE team. Here we see the Sun in different colors or wavelengths, which offers a glimpse into the different layers of its atmosphere. Seeing the multi-wavelength 3D view of the Sun from any part of the solar system is another innovative result from the SPICE team. As we continue, we can choose to observe the Sun's temperature, density, and where the energy is coming from in the solar atmosphere. This is the first time that these quantities have been measured in 3 dimensions. Finally, as we approach the red planet, we can see the Sun from a Martian perspective. The irradiance monitor now shows the solar irradiance as measured from Mars. This blend of rotational 3D views of the Sun, measurements of its physical quantities, combined with changing solar irradiance along a hypothetical path from Earth to Mars, built taking advantage of our constellation of satellites, is the result of our work this year.
But how can we now validate and show that our 3D and irradiance model of the Sun represents physical reality? Well, our method provides unprecedented views and that there are currently no direct observations for comparison. Instead, we make use of a physics-based simulation of the Sun from the solar eclipse in April earlier this year. This allows us to validate our 3D model using the simulation and simultaneously the estimation of density and temperature in the solar atmosphere. To validate our irradiance estimations at different points in the solar system, NASA's Solar Dynamics Observatory mission provides us with irradiance measurements from Earth's perspective. The orange line in the figure on the right-hand side shows the actual measurements, and the blue line our irradiance estimations. As we move towards Mars, we will be able to compare our irradiance estimation from the 3D Sun reconstruction with actual irradiance measurements from NASA's MAVEN mission, which measures solar irradiance from Mars perspective. This will allow us to directly compare our irradiance model with real measurements from 2 points in the solar system.
As we reside inside the atmosphere of the Sun, it is critical to understand its features and large-scale properties. Orbiting satellites have provided never-before-seen images of the solar corona and other solar features. We can now take advantage and enhance these observational resources by utilizing artificial intelligence to simulate views where satellites do not exist. Here, we leverage NASA's satellite missions, without which our work would not be possible, that provide views of the Sun from different viewpoints, as well as in different wavelengths, to create a novel 3D model of the Sun. Now we can study multidimensional solar phenomena and inform future missions in space, such as launching a constellation of satellites to get insight on key positions around the Sun. By learning and integrating data from multiple sources, we can enhance the capabilities of satellites in space and inform future missions. Speaking of missions, humankind has already sent tens of thousands of instruments into space, both robotic and human-driven, that continually get more advanced and far-reaching. In this current age of space exploration, we are in need to understand the space around us and how we can protect ourselves and our technology to enable unrestricted scientific discovery. Here, our model uses the capability of our satellite fleet to create virtual satellites that can estimate quantities from any point around the Sun, including Mars. Our virtual Irradiance instruments can also be added to any EUV imager, enhancing our current capabilities to capture solar activity. Our approach not only extends to heliophysics, but lays the foundation for future coalescence between real observed data and state-of-the-art computational methods. It is not without the Stereo, Solar Orbiter, MAVEN, SDO, and all the instrument teams that make projects like ours possible. Thanks to them, we can use AI as a critical tool to aid and protect our future missions to the Moon, Mars, and beyond. We want to thank the Predictive Science team for sharing their MHD simulations with us, all of our commercial and AI partners, our faculty mentors, and the community of the Frontier Development Lab. We look forward to what discoveries lie ahead. Thank you.